Okay, so we are now at 100 rubber bands. There's still no signs of tear, no deformation, it's not leaking anything else. I expect it to start leaking at around 200 or so. And it stops. Okay, so we're now at 150 rubber bands. Still nothing. I honestly don't know if it'll start leaking at 200 or not. Okay. 196. 197. 198, 199, 200. So we're at 200 rubber bands. No leaking is showing. No visible anything is showing. If I put it up to my ear, I can hear something, but I don't know if it's a rubber band or the watermelon. If it's a rubber band, then this watermelon might be indestructible. 250 rubber bands, still nothing. I'm ready to call Guinness World Records and find out how many rubber bands a watermelon is supposed to hold, and maybe I can enter it to the Wall of Fame. Okay, so we're at 300 rubber bands. There's clearly some deformation. The watermelon is now looking the way that I like it, curvy, just like my women. So, we're doing good so far. And there's some more vigorous leaking on the sides. Shouldn't be too much longer, I hope. Unfortunately, we didn't get to capture the explosion. I was hoping that it would explode at around 400. It kind of just blew up at 302 though. So here we got the watermelon core with a ball of rubber bands around it. And then, yeah, so it took 302 rubber bands to explode a watermelon. At least this one. And then here's the aftermath of it. But I guess you could say that this experiment has been successful. You've seen the watermelon explode. Now we're going to look at how much force it took to explode it. So we took the rubber bands, we measured their lengths, and then we put some weights on them, and we saw how far they stretched. And with the weights, we were able to find the force of the weight by doing the G times M, or the force of gravity, which was the only force acting upon it. And then we took the force, and we took the X, and we made a graph with it, and we used that slope to find out what the spring constant of it was. So once we got the spring constant, we did it with 5 different rubber bands using the same amount of weights on each of all of them, and we got an average K of 105.8974 newtons per meter. Now, in order to find out the diameter of the rubber band, we figured out the circumference with a tape measure, and then plugged it in. 66 equals 2 pi r, which is what we're trying to find, and we got r equals 10.5 centimeters. With those centimeters, we were able to find out that the x of the rubber band was 12 centimeters, or 0.12 meters. And then we plugged in the spring constant with the X, and that gave us a force for each rubber band, which is 12.7. And then after that, once we multiplied it by the amount of rubber bands that we had to use, which was 302, we got a total force of 3,837.72 newtons. Now, the variables of this experiment are the fact that each watermelon has a different toughness, different thickness, everything else, and as well, the reproducibility completely varies depending on the type of rubber band that you use. The other part of it is that when we did this experiment, when we found the K, we were only focusing on the fact that the rubber band was stretching in one direction. Whereas with the watermelon, the rubber band is stretching in all directions, therefore applying forces on each directions. So while this force is enough to burst a watermelon, it is not the minimum amount of force required.